Hi everyone, and welcome back to our next video in the Lab 3 video series. In this video, I'm going to start off by going through various examples related to determining the Fourier series coefficients. So first, let's consider a very simple example. Consider the signal x of t equals sine of omega naught t, where the angular frequency is omega naught. And suppose that we want to determine the complex Fourier series coefficients. We can actually do this in three different ways. The first way, which is pretty much the brute force way, is to use the formula Cn equals 1 over t naught times the integral from 0 to t naught of sine of omega naught t times e to the minus j n omega naught t dt. So I'm going to apply Euler's identity that e to the minus j n omega naught t equals cosine of n omega naught t minus j sine of omega naught t. And so this integral becomes 1 over t naught times the integral from 0 to t naught of sine of omega naught t cosine of n omega naught t minus j sine of omega naught t times sine of n omega naught t, and this whole thing times dt. Now in general, the integral over one period of sine of n omega naught t cosine of m times omega naught t dt always equals 0 regardless of the values of n and m. So we can get rid of this first term here in the integral, which would give us Cn equals 1 over t naught times the integral from 0 to t naught of minus j sine of omega naught t times sine of n omega naught t dt. We'll now look at three cases: when n equals 1, when n equals minus 1, and n is not equal to 1 or minus 1. Case 1 is n equals 1. So C1 equals 1 over t naught, the integral from 0 to t naught of minus j sine square of omega naught t dt. And since in general the average value of sine square over one period is 1/2, then the integral over one period of sine square of omega naught t dt will be t naught over 2, which means that C1 equals 1 over t naught times minus j times t naught over 2, which equals 1 over 2j. And you can essentially follow the exact same procedure for n equals minus 1, which is case 2, and you would end up with c minus 1 equals minus 1 over 2j. And lastly, case 3, for n is not equal to plus 1 or minus 1, we would again end up with Cn equals 1 over t naught times the integral from 0 to t naught of minus j sine of omega naught t times sine of n omega naught t dt. But using the fact that in general, the integral over one period of sine of n omega naught t times sine of a different constant m omega naught t dt, that is always equal to 0 for n is not equal to m, which means that this entire integral here evaluates to 0. So if we collect the results from the three cases, we have Cn equals minus 1 over 2j if n equals minus 1, 1 over 2j if n equals 1, and 0 if n is not equal to plus 1 or minus 1. Now, a second and much faster way that we could have done this is simply use Euler's identity from the start. So sine of omega naught t equals 1 over 2j times e to the power j omega naught t minus 1 over 2j times e to the minus j omega naught t. And so this tells us immediately that the complex exponential Fourier series representation only consists of the fundamental harmonic corresponding to n equals 1 and minus 1, where C1 equals 1 over 2j and C minus 1 equals minus 1 over 2j. And since we only have the fundamental harmonic, all the rest of the Fourier series coefficients are 0. And lastly, a third way to do it is to look at the sine-cosine representation of the Fourier series. Recall that for this Fourier series representation, x of t equals a naught plus the sum from n equals 1 to infinity of an cosine of n omega naught t plus bn sine of n omega naught t. So comparing this with x of t equals sine of omega naught t, we see that the Fourier series only consists of the first or fundamental harmonic. So a0 equals 0. And the coefficient of cosine of n omega naught t is 0 for all n. And bn equals 1 if n equals 1 and 0 otherwise. Now from this we can very easily find Cn. So Cn equals 1/2 an minus jbn. So when n equals 1, C1 equals 1/2 a1 minus jb1. a1 equals 0 and b1 equals 1. So C1 equals 1 over 2j. Also, keep in mind that since x of t is real, we know that there has to be conjugate symmetry, which tells us that C minus 1 equals C1 conjugate, which equals 1 over 2j conjugate. And whenever you take the conjugate of a complex number, you replace j with minus j. So C minus 1 equals minus 1 over 2j. And since an equals bn equals 0 for all n is not equal to 1, Cn, which equals 1/2 an minus jbn, also equals 0 for all n is not equal to 1. So in this example, we saw 3 different ways for computing the Fourier series coefficients of x of t equals sine of omega naught t. Now let's look at a slightly more complicated example. Suppose that x of t is given by x of t equals 1 plus sine of omega naught t plus 2 cosine of omega naught t plus cosine of 2 omega naught t plus pi over 4. Now our goal is to determine the complex exponential Fourier series coefficients. Now integrating directly using Cn equals 1 over t naught times the integral from 0 to t naught of x of t e to the minus j n omega naught t dt, that would be quite a bit of work, and having to write each sine and cosine as either a sum or a difference of 2 complex exponentials through Euler's identity could also get quite a bit messy. So I'm going to follow similar to the third method we saw in this previous example, but instead of comparing x of t directly to the sine and cosine representation as we did here, I'm going to compare x of t with the amplitude phase representation. Now to do that, we need to simplify x of t just a little bit. So I'm going to use the identity that a cosine of omega naught t plus b sine of omega naught t equals I cosine of omega naught t minus theta, where I equals square root of a squared plus b squared, and theta equals tangent inverse of b over a. So using this identity, we have x of t equals 1 plus sine of omega naught t plus 2 cosine of omega naught t evaluates to square root of 2 squared plus 1 squared, which is 5, times cosine of omega naught t minus tangent inverse of 1/2, plus the third term, which is cosine of 2 omega naught t plus pi over 4. Now, if we compare this with the amplitude phase representation of the Fourier series, we see that we have a DC component, so C naught equals 1. For the fundamental harmonic, magnitude of C1 equals square root of 5 over 2, so 1/2 of this coefficient here. The angle of C1, which equals phi1, equals minus tangent inverse of 1/2. And for the second harmonic, magnitude of C2 equals 1/2. And the angle of C2 equals phi2, which equals pi over 4. And if we put these results together, this implies that we still have C9 equals 1. C1 equals square root of 5 over 2 times e to the power minus j tangent inverse of 1/2, which, if you draw your right triangle, evaluates to 1 minus 1/2 j. And similarly for C2, C2 equals 1/2 times e to the j pi over 4. And all I had to do is use Euler's identity, and you would get square root of 2 over 4 times 1 plus j. Now that we have C1 and C2, since x of t is real, the complex exponential Fourier series coefficients exhibit conjugate symmetry, which means that C minus 1 equals C1 conjugate, which equals 1 plus 1/2 j, and C minus 2 equals square root of 2 over 4 times 1 minus j. So if we combine all of these results, we see that Cn equals square root of 2 over 4 times 1 minus j, if n equals minus 2, 1 plus j over 2, if n equals minus 1, 1 if n equals 0, 1 minus j over 2, if n equals plus 1, square root of 2 over 4 times 1 plus j, if n equals plus 2, and 0 otherwise. And these are the complex exponential Fourier series coefficients for x of t. Now, in order to sort of visualize graphically the complex exponential Fourier series coefficients of x of t, we're going to look at plots of the magnitude line spectrum and phase line spectrum of Cn. The magnitude line spectrum is a plot of the magnitude of Cn versus n, and the phase line spectrum is a plot of the angle of Cn versus n. And both of these are a two-sided line spectrum. So as you can see in the figure, we have the magnitude line spectrum for magnitude of Cn on top, and the phase line spectrum for the phase of Cn on the bottom. In the magnitude line spectrum, we have a DC component of 1 corresponding to n equals 0. For the fundamental harmonics, we have magnitudes of approximately 1.118, which is square root of 5 over 2. And for the second harmonics, we have magnitudes of 0.5 or 1/2. And as you can see in the plot, for all the nth harmonics corresponding to n is greater than 2 and n is less than minus 2, the magnitude of the complex Fourier series coefficients are all 0. We can also look at the phase line spectrum. So the phase of the DC component is 0, since the DC component is always a real quantity. We have the phases of the first harmonics. Note that the phase at n equals 1 is negative, whereas the phase at n equals minus 1 is positive, and conversely, the phase at n equals 2 is positive, whereas the phase at n equals minus 2 is negative. And similar to the magnitude line spectrum, for all nth harmonics corresponding to n is less than minus 2 and n is greater than 2, the phase of the Fourier series coefficients are 0. Now notice how the magnitude line spectrum is symmetric with respect to the y-axis, whereas the phase line spectrum is symmetric with respect to the origin. And this makes sense due to the fact that x of t is real, So the complex exponential Fourier series coefficient Cn exhibit conjugate symmetry. And according to conjugate symmetry, C minus n equals Cn conjugate. So the magnitude of C minus n equals the magnitude of Cn, which is why the magnitude line spectrum is symmetric with respect to the y-axis. And the angle or the phase of C minus n equals minus the angle or the phase of Cn, which is why the phase line spectrum is symmetric with respect to the origin. All right, so let's look at a third and final example, which is determining the Fourier series coefficients of a periodic square wave. And so here's a rough depiction of what our periodic square wave looks like. From this plot, we can define x of t over one period as x of t equals 1 if absolute value of t is less than t1, and 0 if t1 is less than the absolute value of t is less than t over 2. The fundamental period of this square wave is t, and the angular frequency is omega naught equals 2 pi over t. So to determine the Fourier series coefficients of x of t, we're going to use the integral formula to calculate Cn, but instead of integrating from 0 to t, we're going to choose the lower bound of our integration limits to be minus t over 2, and the upper bound to be plus t over 2. So let's first evaluate C naught using these limits of integration. So C naught equals 1 over t times the integral from minus t over 2 to t over 2 of x of t dt. And during this interval, this equals 1 over t times the integral from minus t1 to t1 of 1 times dt. And this evaluates to 2 times t1 over t. And C naught is interpreted as the average value of x of t, which in this case equals the fraction of each period during which x of t equals 1. Now, for n is not equal to 0, we have Cn equals 1 over t times the integral from minus t over 2 to t over 2 of x of t times e to the power minus j n omega naught t dt. This equals 1 over t, similar to the previous case, times the integral from minus t1 to t1 of 1 times e to the power minus j n omega naught t dt, which equals minus 1 over j n omega naught t times e to the power minus j n omega naught little t, evaluated between minus t1 and t1. And this equals minus 1 over j n omega naught big T times e to the power minus j n omega naught t1 minus e to the power j n omega naught t1. And we can rewrite this as 2 over n omega naught capital T, distribute the minus inside and then multiply by 2 on the numerator and 2 on the denominator, as e to the power j n omega naught t1 minus e to the power minus j n omega naught t1, this whole thing over 2j. Now notice that this quantity in brackets here is sine of omega naught t1. So therefore Cn equals 2 times sine of n omega naught t1 over n omega naught t, which since omega naught times t equals 2 pi, we can rewrite this as sine of n omega naught t1 over n pi for n is not equal to 0. So let's look at a spectrum of the complex exponential Fourier series coefficient Cn for this periodic square wave. Now, in this specific case, the coefficients Cn are purely real, so we can look at a plot of Cn versus n directly, as opposed to looking at the magnitude line spectrum. So here's a plot of a scaled Fourier series coefficient, t times Cn, for the periodic square wave, with t1 fixed, and then several different values of t. In this first plot on top, the period t of the square wave is 41, which means that x of t is a square wave that is 1 for half of its period and then 0 for the other half period. In the second plot, the period t of the square wave is 81, which means that x of t is a square wave that's 1 for a fourth of the period and 0 for the remaining 3/4 of the period. And the third plot corresponds to t equals 16 times t1. All right, so this is it for this video. And in the next video, we're going to look at the convergence of the Fourier series and how this relates to signals with discontinuities like the square wave in the previous example.